All right, good. Well, thanks so much, everyone. I've been wanting to do a talk for you for a while. Like I say, I've been in the Python community relatively recently, or joined it relatively recently, but been in the Chicago meetup space for a long time. Like if you go to the GoTo conference, or if you happen to go to the Scala conference, or some of the big data, or Scala meetups rather, and some of the big data events. Um, so I'll have most of these links at the end. But basically, Anyscale is the company that was spun out of Berkeley to develop Ray, which was a research project that I'll describe in this talk and why you might be interested in it. There's a couple of big trends going on right now that kind of really were the inspiration for Ray. One is this interesting picture that the size of neural networks, is what this is really plotting, have grown 35 times every 18 months. This is a log plot. And for comparison, Moore's law is famously 2x every 18 months. So you can do the math. We're obviously outstripping the ability of our hardware to keep up. Of course, that's been a general rule for forever in computing. But what it really means is we need to go distributed if we're going to meet the compute requirements we have. And of course, as we were just discussing, Python is once again on a rocket ship of adoption, driven in large part by the kind of insane interest really in ML, AI, and general data science. And it's really proven to be a great language for all of this stuff. And I think the reason Python is so successful is it's a very approachable language for people who are more interested in focusing on the problems that they're trying to solve and less on sort of language theory and that kind of stuff. And for me, it's interesting to compare the two because I do come from the Scala community, which is a much more sophisticated language, statically typed and all that. And I can appreciate the virtues of both for their different strengths and weaknesses. But anyway, what it shows is that we just have to keep thinking about how to do distributed Python, not just distributed over the cores and our CPUs, for which we do have a lot of good libraries, but going beyond the boundary of the machine to a cluster and make it as easy and approachable as possible. And that's really the vision that Ray has. So this is sort of a typical group of things that you have to do in the machine learning world. And if you're not doing machine learning or anything like that, I'm actually going to talk a little bit about microservices towards the end. But just to give you a flavor for kind of the compute problems that arose. In a typical data science world, featurization is about figuring out what characteristics of my data are actually useful for analysis or predicting future behavior. A lot of what we do now is done in the context of stream processing, hyperparameter tuning. I'll explain what that is in a minute. Model training you probably heard about, and simulation, like if you're doing so-called reinforcement learning, which I'll also describe briefly, you often are running like a game simulator or a robot simulator, something like that, to design a thing that can navigate through that environment in the most effective way. And once you've built this model, then you have to serve it. And all of these things typically require distributed systems because of the scale of the problem. And you can see all these icons for popular tools that are focused on part of the space in one sense or another. The vision of Ray is that maybe we can build a common framework that can sit underneath all of these kinds of problem areas, something that's relatively approachable. It's currently targeted towards Python, but it's actually designed in such a way that we can add support for other language APIs. And for example, Java is probably going to be the first one we support. And then on top of that, what actually most people will use will be libraries for training, hyperparameter tuning, and so forth. If you're a regular Python developer, like writing web services or whatever, then you might actually use Ray itself. So what is it like to use Ray? Well, one of the things that we tried to do is make it as intuitive and concise as possible and leverage familiar ideas. So we're all used to writing functions to do particular kinds of work, like these two on the left, where I'm going to have some function that constructs a NumPy array in some way, returns it, and then another function that adds it. Not a terribly exciting example, but simple enough that we can focus on what Ray is doing. To make these things Rayified, if you will, you add this annotation, ray.remote, and what this does is it turns them into what we call tasks. We use that term because now these things can be distributed across a collection of workers across your cluster and then do the work of the computation required here. Do it asynchronously, do it in parallel as a result, and then you can gather the results when you're done. I should say, for completeness, if you tried to type this in and run it, you'd need to do or add the code on the right, which does the imports and initializes Ray. Maybe I should have added you do pip install Ray before all of this, of course. Okay, so how do you actually use these tasks once you've defined them? Well, there's actually a change in the way you invoke them. Instead of saying make array and then argument list, it would be make array.remote argument list. Now, Python's a very malleable language. We could have designed Ray so that you didn't have to change the way you call these now tasks. The reason we think it's a good idea, though, to leave this in place is so that just by reading the code, it's sort of self-documenting. You know that this is a remote task invocation as opposed to a normal synchronous function call. And what it's actually returning is the ID for a future. It'll be, again, this is an asynchronous task. It could be running on any machine in your cluster, but this ID will give you a hook for retrieving the value later on once it's done. So we could call it again and get another ID. And then we could call this add arrays task to actually, add the two arrays together. And that returns yet another ID that we can then get the final result from. But there's a couple of interesting things going on here, though, that are designed to make it as easy to use as possible. The first is that we actually have a dependency between these tasks. We can't execute add arrays until the other two are done, but you don't have to worry about that. Ray detects these dependencies and automatically sequences them for you. So even though you fired off these 3 asynchronous tasks, the last one, add arrays, will not be scheduled and executed until the other two are done and the results are available. And the other thing that this does automatically for you is notice that I pass those IDs to add arrays rather than passing NumPy arrays. I didn't have to pull out the objects and pass them in the correct way. Ray handles that automatically for me. So that just a couple of things where with relatively simple modifications to your Python code, you can get this asynchronous execution. And then to actually get the value when you're done, you make this blocking call that will wait until ID 3 can actually return the object that it's referring to somewhere in the cluster. Now, one thing we haven't talked about yet is what about distributed state? This is one of the biggest challenges writing distributed systems as you start having your state spread all over the cluster, and it can be hard to keep track of, hard to manage. So once again, we try to leverage a familiar idea, which is classes. These are an encapsulation of state and methods to operate on them in hopefully some intuitive way. So this is a simple example of a class that just does a count. Every time you call increment, it increments an internal state value, and then you can retrieve it to see what's going on. There's actually a flaw in this example. I just noticed, I've done this talk several times. When you use Ray, you actually have to add a getter method to retrieve the value. You can't just call self.value to get it. But anyway, conceptually, it's very much the same. Anyway, so what are we going to do? We add the annotation again, and now we turn this into an actor. Now, if you haven't heard of the actor model of concurrency, it's really a very beautiful, simple idea. It's the notion that each of these actor instances are like autonomous agents. I'm going to send them messages, in this case, increment, to do work, and the actor system will guarantee that it's done in a thread-safe way. So if this thing's being hit from all over the cluster, you won't get like invalid state corruption because you didn't handle thread safety. The actor system handles this for you. It's been used in a lot of systems. Those of you that happen to know about Erlang, for example, or maybe Akka in the JVM world, will know that those are examples of actor systems. So that's where the word comes from. And you call it pretty much the same way. You use this remote annotation on the constructor, on the method calls, and then you can also retrieve the values when they're done. Notice you can pass a list of IDs to ray.get if you want to. You don't have to just do it one at a time. Okay, let's take a look behind the scenes a little bit to see what's actually going on. I always love to do this when I'm encountering a new system so that I really have more of a sense of what's going on and more empathy for the machine, if you will. So let's imagine we have a 3-node cluster, and on each of these nodes are these processes that are running that I'm going to describe. And what we're going to see is how this particular scenario of tasks might actually be executed. So first, let's imagine that the driver for this program, this regular Python program, is running on node 1. it will send these tasks to the local scheduler on that node. This is a array task that's running in the background. And it will return the IDs immediately because that's just firing off these asynchronous processes, so I can go on and do other stuff while these things are running in the background. And this global control store is kind of like where all the metadata is kept so that the Ray system knows where everything is running and so forth. So suppose the local scheduler decides I've got space on one of these local workers, so I'll schedule this one to run locally. But maybe it decides it needs to schedule the other one on another worker. So I kind of cut a few corners here. It actually communicates to the other scheduler that then schedules it on the worker. Now, when these two finish, they're actually going to write their objects to this object store. This is a in memory. It's actually shared memory, as we'll see in a second. It basically leverages Pandas Plasma object store, if you're familiar with that. Now, as I said before, because these tasks have finished, I can now schedule add arrays. Let's suppose I schedule it on the same node. Now, it doesn't need to copy object one into its local memory space. It can actually just read it because it's in shared memory. So if object one were enormous, then that could be a big performance boost if we were doing this over and over again a lot of times. Now, object two obviously isn't on the same node, so we're going to have to copy that over, and now it can be read from, again, shared memory. And then when add arrays is finished, it writes its result back to object three. And then we can call ray.get to fetch that object using ID3. And we're basically done. So that's sort of what goes on when you run in a cluster. When you're actually running on your laptop, it's basically like node one by itself is running. It's a little bit lighter weight, but you're still basically running in a concurrent way. And you can actually get a lot of performance boost just by being able to spread the work over all of the cores in your laptop or workstation or whatever, even if you don't have a cluster. Okay, what about if you wanted to migrate to Ray? Maybe you've already written a lot of stuff in some of the traditional multiprocessing libraries like multiprocessing.pool or joblib or async. Well, it turns out we've actually implemented these in Ray as well, these APIs. And normally it's just a drop-in replacement where you just change the import statements. And what you actually get then is the ability to simply have these constructs scale over a cluster instead of being bounded by the node that they're running on. And I should mention, in all full disclosure, there is extra activity going on that Ray is doing because it's doing this distributed stuff. So in some cases, if you only need to be on a node, it won't necessarily be faster. It could even be a little slower because of the extra overhead that Ray has to have for all the work it's doing. We're aware of this. We're trying to get rid of this, so it's just a no-brainer to use these implementations. But that's one thing to think about if you were deciding whether or not to switch. And the overhead difference is not that big, but if you're really, really concerned about performance, you might be thinking about it. Oh, I guess I should have mentioned, there's a couple of blog posts at the bottom. I'll make these slides available that you can read more about how these APIs work. All right, let me talk a little bit about the libraries for machine learning, a couple of them that are built on Ray. I think most people who are using Ray will be essentially like most people using Python. They won't necessarily understand or have to understand the internals of Python. They're just using this abstraction on top. Similarly, a lot of people will use these machine learning libraries, never actually drop down to the Ray layer, but they'll of course be using Ray under the hood. So here's that graph again or chart, if you will, of features or things that you have to do in typical machine learning and data science environments. And these are 4 of the libraries that we've implemented using Ray. Ray SGD was actually just announced this week in a blog post on our website. Serve was recently announced as well, and we haven't even done an icon for it yet. What I'm going to talk about are RLib and Tune. So RLib is for reinforcement learning. It's perhaps our most popular library. It's certainly the biggest, most sophisticated of our libraries. If you haven't heard of reinforcement learning, it's really, at least at a conceptual level, very simple. You have some agent working in an environment and it wants to learn the best way to navigate through that environment to maximize its reward, whether it's playing a game or learning to walk, like the little weird icon with the robot on the bottom, or learning if it's a real robot and it needs to learn how to pick and place things. That's basically the idea. And the way that you train these things is that you just have them do this exercise over and over and over again, and they learn what things seem to work better than others and eventually triangulate to what is hopefully an optimal solution. One of the most famous examples is the AlphaGo system that beat the world's best Go player. Um, a few years before this happened, people assumed it would be a long, long time before machine learning systems got good enough to beat a system like Go, which has a huge state space. But they basically did it by using a neural network to help make decisions. They observed the board state. They decided where next to place the stones on the board. And in this case, the reward was either win or loss, 1 or 0. So you've probably heard about a lot of these applications of reinforcement learning, like training a robot to walk or training a car to avoid pedestrians or winning games. We are starting to see some interesting applications in industry outside of these. A couple of my favorites are on the left. There are a number of companies that are starting to look at process automation. Like, think about how a factory floor works or how something complex is assembled. How can we optimize these processes? How can we optimize like chemical control processes and so forth? Um, Another interesting one is advertising and recommendations are kind of related. They're finding ways to use using reinforcement learning to improve the quality of these things and deal with the fact that they're often dealing with enormous state spaces. Like, if you think of the classic way of doing recommendations, you have a massive set of customers and the things that they've rated, movies, let's say, and then you come along and you want a recommendation, so they try to find how you match. And it's a giant matrix, linear algebra problem, and it's actually just too big when you're somebody like Netflix or whatever. So they're actually using RL to improve the quality of these things and get around some of the compute challenges of them. And then finance, of course. If you think about the stock market, it's a time varying system, just like a lot of these other sort of games or systems we're talking about. It's also a candidate for RL. So what RLlib tries to do is, you have these applications on top. You have several sort of general big strategies you can follow, like, do I have just a single agent in the environment or collaborating agents? Are they structured hierarchically? Offline batch is kind of an interesting one that I think is up and coming. It's the case where, I can't run my chemical factory over and over again to train your silly system, but I can give you a massive set of logs for how it's behaved in the past. So maybe you can train something from that. So the offline batch is the idea. RLlib tries to give sort of a uniform API for all of these choices, and then it has a ton of algorithms that have been published under the hood. And of course, it's all running on Ray to get maximum scalability. So if we go back to this picture for just a second, RLlib was really kind of the genesis of Ray in a way. Reinforcement learning had some unique challenges that just weren't being addressed very well with the tools that were available to these guys at Berkeley at the time. And if you think about what's required on this problem, it's a very diverse set of compute kind of patterns, memory access patterns, and so forth. For example, the simulator, the game engine, or the robot simulator, the factory floor simulator. These things are more like regular state machines or web service applications we're used to writing, which could be a lot different than some of the other things we're doing. The agent might also be very complex. It might have some big decisions to make or whatever. Then we've got our usual neural network stuff, the whole way that we train these things, the way that we manage the data, the whole parameter set, with some of these networks getting into the millions and billions of parameters, excuse me. So the point is, finally, that we have to not only handle all these different compute patterns, but we have to do it over and over and over again, because we're trying to learn the best approach. And train as we go. And that means we have to play these expensive processes over and over again. So we need things that do this as optimally and efficiently as possible, but also cover a wide range of compute requirements. And this was really the big inspiration for Ray, was this kind of flexibility, efficiency, and scalability was what drove the creation of Ray. This is a eye chart of some of the RL algorithms available in RLlib. If you've done any work with it already, you might recognize some of these terms. These are all links to the documentation. You can even play with this in Amazon SageMaker if you want. And now let's talk about Tune. This is the hyperparameter tuning system in Ray. So what's Tune all about? First of all, what is hyperparameter tuning? Well, here's the most trivial example I could think of. If you've ever done k-means clustering, which is, I've got a bunch of data and I want to find out where the clusters are, the first big decision is what should k be? This illustration is from Wikipedia, and in this case, k is 3. I'm looking for 3 clusters. But maybe I should try 5 or 2 or something like this. So k is sort of the hyperparameter. And then when we actually find where these clusters are, the parameters that define those clusters are the parameters. So that's what we mean by hyperparameter tuning. It's what is the structure of the system that we're running, and then we actually train it to fit our data. And it really has become a problem when we've been dealing with these big neural networks. Every number you see on this picture is a hyperparameter. The size of these layers in the network, actually how many there are, whether they're max pooling or dense, all of this stuff are the sort of choices that we could make when we're deciding what model would actually fit our data best. And if you think about the combinatorial explosion you've got here, if you wanted to just naively try every combination, you could run forever. So a lot of the art of hyperparameter tuning is making intelligent guesses and using algorithms to try to, prune off things that don't seem to be working that well so that you don't waste resources doing, training exercises on those. And you instead triangulate to a good solution. And then after you've got the good solution, namely the hyperparameters, the structure of your neural network, then you can actually train it with the data, the full training regime to actually create the model parameters that will then be used for scoring or recommendations or winning AlphaGo or whatever. It does matter. This is a case of just a simple example of 3 different runs where the blue one gives the best result, the pink one gives the worst, and it's all just a difference in their hyperparameters. So we want the best model. Resources are very expensive, especially if they're GPUs, and it's very time consuming to do training. So that's what Tune is trying to solve for us. And it effectively handles a lot of the parallel runs that are required to try different configurations. It's designed to be very easy to configure a training job or hyperparameter tuning job. You basically say what model you're training, a few parameters, the kind of optimization strategy to use when finding the optimal hyperparameters, and it's integrated with a lot of the popular frameworks. It's integrated with Tensor Board, so you can see what the parameters look like when you're done. And it's also very aware of the specific requirements for deep learning neural networks, such as scheduling to GPUs, integration with the popular frameworks, and so forth. All right, let me finish with a discussion that maybe would appeal maybe to those of you that don't care about machine learning, and that is, what about microservices? Now, first I should say microservices are getting sort of a backlash right now. You may have heard that Uber has announced they're going to macro services. Certainly people have drank the Kool-Aid a little too much on them, but you can strike the word micro if you want. What I'm going to describe is pretty much true for any sized services you care about. There's a couple of ways you could talk about microservices. One of their goals is to kind of separate responsibility. Like, one microservice might be doing DNS resolution, another one might be handling authentication, that kind of stuff. And one of the reasons you like to separate these things is you might need to manage them in a separate way. Some of these microservices might need a lot more instances than others because maybe they do expensive or hard calculations, or maybe they just hold or handle a lot more load. Sometimes you have to change them out more frequently because they might be evolving more rapidly. But the key point really here is that you've got to manage all these instances explicitly. And so it sort of raises a question, well, why do I have all these instances in the first place? Why are they necessary? Well, there's 2 reasons. One, of course, is that you might want multiple instances of something running for resiliency in case one of them fails. That's always important. And the other reason is just that you run into the boundaries of machines and you end up having to spin up another instance somewhere else. What if we could get rid of that? Well, that's the whole idea that here for how Ray could be really useful is that, and again, this is like, a vision more than a complete reality. There's a lot of details here that you'd have to get right. But you could go back to a little bit more of a model where you have one logical instance for each of these microservices, and then you use Ray to scale across the cluster. So effectively, you've created like one giant machine out of all of the nodes in your cluster. And that reduces the need to have explicit management of individual instances. We're thinking a lot about what this really means. I think this is a really good starting point that you could use today, but there's a lot more here that I think Ray can help us to make it a lot easier to build these highly distributed systems that are easy to manage, because it can do a lot of the sort of boilerplate for us behind the scenes. Let me mention one thing. How does this play with Kubernetes and stuff like that? Ray is very fine-grained. So really these actors just run as if they're inside nodes, whether they're physical machines or virtual machines or containers or whatever. It's just a different level of granularity, so it plays very well with a system like Kubernetes. In fact, there's tools inside the Ray distribution for working with Kubernetes. So in conclusion, we think it's a really new but already state-of-the-art tool for distributed computing, especially for Python developers. This is a bit of a tagline, but we think it's the shortest path from starting to work on your laptop and then going to the cloud. But it does let you run really complex, really big distributed tasks on large clusters with relatively simple coding constructs. Okay, here's some links for you. We do have some online events happening this summer, our so-called Ray Summit Connect, and then we're trying to do Ray Summit in November. It was supposed to be in May. For obvious reasons, it got pushed back. But check out anyscale.com/events for information. I'll tell you that there's going to be a lot more details posted next week. It's a bit sparse right now, but you can sign up for information. We are actually hiring. If you want to go to our jobs page, if you want to learn more about Ray, go to ray.io, and you can spam me at this email address. So I'll go out of full screen mode and take any questions anybody has.
Awesome. Thanks so much for that talk, Dean. So we do have a few questions. Folks, just going to add that to the screen. So folks are wondering what the relationship is between Ray and Modin. It's like the Pandas project.
Yeah, that's a good question. So Modin is a research project in Berkeley that's using Ray, and it's also using Dask to try to put a more faithful API of Pandas, and I'll explain what I mean by that in a second, either on top of Ray or on top of Dask. And by more faithful, I mean, I think all of the Panda-like implementations out there like Dask are usually a subset of the actual full Pandas API. I did mention Dask. Al, I don't know if that question came up. It usually does. What's the similarity or difference between the two?
Yeah, that question is also there.
Yeah, Dask is really great if you want to do distributed pandas, distributed NumPy arrays, that kind of sort of data analytics, traditional data analytics. We think Ray is better for more fine-grained, more general purpose distributed computing, like I described when I was talking about reinforcement learning. So they sort of compete in a way, like I said, and if Modin were a more mature project, then maybe they would compete more directly. But right now, I would go with Dask for what I just described and go with Ray for the kind of general purpose compute.
Okay, awesome. There's also some questions around schedulers. So is this scheduler fault tolerant?
That's a very good question. You can basically set a flag now to have any actor that dies restarted. There isn't a whole lot there yet, though, in terms of like really high reliability, high availability sort of resilience. We're just getting started on building out the capabilities. Excuse me. For example, like I mentioned, I used to be in the Scala ecosystem, and there the big tool was Akka, and it had a very sophisticated model for declaratively specifying what to do to recover. We're still working on that in the Ray world. It's not quite there, but you can do some basic stuff already.
Okay, awesome. And the second question I see around schedulers is, how does the scheduler prioritize work? How do you make sure one worker doesn't take up too much CPU time?
Yeah, good question. I didn't show this, but you can actually, for those Ray remote annotations and also in the initialization of Ray when you start it up, you can specify resource constraints. So a common thing to do, not only constraints, but resource requirements. Like you could say this function or this task requires a GPU, and then Ray will make sure that it schedules on a node with a GPU. So it does have constraints that it will try to respect. One thing they've just been implementing, actually, this was a problem in the JVM forever, was making sure that they respect container restraints and not just node constraints. If those of you that have worked in the JVM at all may know that for a while Java would just blow past the constraints of a container and just look at what the node offered. Obviously, not a good thing. That's the same sort of thing that we are working to ensure we obey.
Okay, great. And there's a question about the implementation. Before we get to that, if you do have questions, please ask them in the chat and we will try to get to as many as we can. And so this question about implementation is, why not implement Ray as a backend to the standard library concurrent.futures, something like the thread pool executor or the process pool executor?
That's a really interesting question. We did do multiprocessing.pool, as I mentioned. I think it was a decision around how low in the granularity stack to go. I don't honestly know the answer to this question, why they didn't do it this way. And I'm not that familiar with the implementation, so there may be some of this in there already. But I will say one of the things they've done recently is move a lot of the logic of Ray into the C++ core to make the Python API as thin as possible. And the main reason for that was to make it easier to support other languages. So if you decide you want like a Rust API on top of Ray, that there's less work to do.
And you were mentioning there were plans. What are the next languages on the horizon?
So there's actually a Java API that our biggest user, which happens to be Ant Financial in China. This is like the equivalent of Stripe over there, a spinoff of Alibaba. They actually implemented a Java API that is, it's actually in the code base, but it's considered experimental because we're still iterating on the API itself. Other than that, we've talked about C++. We've had some interest in Rust, which I'd love to see because I think Rust is kind of an interesting language. But Python is just so big, and we're mostly kind of focused on the machine learning world. That Python is really going to be where most of our energy goes for a while.
So are there plans to go to R? Because I know it's used quite a bit in that same space as well.
We haven't had any requests that I'm aware of for R support. And I think it's probably just a matter of limited resources, and everyone in our team is just kind of a Pythonista and not that familiar with with R.
Awesome. So we have Scott asking in the chat, does Ray tolerate dynamic scaling of a cluster? For example, adding or removing a node?
It does actually. In fact, one of the nice features they built into Tune is the ability to use spot instances, and it will recover. Going back to that question earlier, there is some sort of large granularity recovery that's built into some of the libraries that's now being moved into the core. I mentioned how expensive hyperparameter tuning can be. If you can use spot instances, that's obviously a big win because it's a lot cheaper. You'll just lose some of your work periodically. So it is actually Ray itself, and some of the libraries in a more involved way are tolerant of adding and removing nodes in the cluster.
Awesome. I think that's all the questions in the chat. Well, we do have the question of the night. I'm sure you're going to say Ray, but besides Ray, what would you say your favorite Python library is?
Yeah, I do like the big machine learning libraries. Like and the ones I've used the most are TensorFlow, PyTorch, and scikit-learn. Those are the ones that are really fun. Bottomless too. I have to say too, I've been using Bokeh a lot lately for graphs, and really enjoying that one as well.
Yeah, it adds a lot of interactivity with barely any work on your side. I love it.
Yeah.
Well, thanks so much for joining us today, Dean. Do you have any final things to say to our broadcast?
I do appreciate the option or the opportunity to speak tonight, and I'm looking forward to when we can all get back together and meet space at some point. So.
Yeah, I can't wait either. We can't wait to have you actually give a talk in person. That would be awesome.
Looking forward to it.
Awesome. Well, thanks so much, Dean. We'll let you go.
All right. Thank you. See you guys.